To motivate the segment tree, the twin structure to interval tree, we need to go back to the original problem that we started with. We have a set of line segments, not necessarily horizontal or vertical, it could be arbitrary orientation, and we want to find those that intersect the vertical line segment. And if you look at the previous solutions, you can see that none of them actually work. This idea of using a three-sided query don't work. You can't capture these line segments that cut diagonally and so on. Okay, so we have to do something different. And the idea here is to build a segment tree, which is very similar to the interval tree, but with very big differences. There are many ways to explain a segment tree, but one way to explain them is to look at the notion of elementary intervals and canonical sets. Okay, so take a look at the endpoints of the line segments, right? So let's say these green line segments are the input, and I look at the endpoints. Draw a vertical line through every endpoint that would decompose the plane into a bunch of slabs. And the region between two consecutive vertical line segments is called an elementary interval. So for example, this blue vertical strip is a one elementary interval. Okay. Obviously, one solution to this problem is to, for every elementary interval, store these line segments in some order and then do a binary search to find the first one that intersect and then walk through them. That's not good. That takes n squared space. A segment tree is a data structure that kind of does the same thing but using n log n space. So let's see how it works. Okay. To have a better understanding, we could project these segments into just the x-axis and just look at them as intervals. Okay, so that's the first thing we do. And now what remains to do is to somehow build a data structure for interval stabbing. Right, so think of them as just horizontal line segment, and now we want to find everything that intersects a vertical line segment. Yeah. Obviously, this is not exact translation because we know how to solve this, but this is just essentially a conceptual representation of these intervals, right? So we can't actually do this transformation yet because we don't know how to handle the coordinates. Alright, so how do the segment tree look like? Think of the elementary intervals of leaves of a binary search structure, where the region of a node, of an internal node, is the union of the two regions of its children. Okay, so in other words, this leaf corresponds to this elementary interval. This leaf corresponds to that elementary interval, and the region of the parent of those two will be that elementary interval. Okay, so by putting these elementary intervals at the leaves, I could build the interval of every internal node, including the root, and the interval of the root will be essentially this entire thing. Okay, so for example, that's the endpoint for that node. Okay. And then for every node that I look at, including internal nodes, I allocate a canonical subset. So this is very similar to the canonical subset that we looked at for the range searching, except the difference here is that in the range searching, the input was a set of points, so therefore a canonical set was a subset of those points. Here the input is a set of intervals, so therefore a canonical set will be a subset of those intervals, right? So the element of the canonical set here is a set of intervals, is a bunch of intervals. So but what are the intervals that are stored in this node? These are the intervals that completely span this range here, so they have to go outside this, but they don't have this property for the parent of this node. In other words, this node is the highest node in the tree when an interval completely spans its region. Okay, so I want to have these two conditions. So for example, if this is the region of this node here, and if I look at the parent, maybe the region of the parent is this big, you'll see that none of these purple intervals span the parent of this node V. They only span the range of V. So therefore they are stored at the node V. Okay. So for example, that's one example. And that essentially defines a segment tree. Note that unlike an interval tree, one line segment could be stored multiple times in a segment tree. Okay. So therefore it is not obvious that the segment how to analyze the space complexity of a segment tree, and that's what we're going to do next.